Welcome to our last chapter in Engineering Economic Analysis. This is exciting. We finally reached it. So we're actually going to be talking about Chapter 9 in this lecture, but we're skipping Chapter 8. So this is really Lecture 8. So don't let that get confusing. So since our last test, we focused a lot on different types of economic analyses. So in Chapter 5, we talked about present worth analysis, Chapter 6, annual cash flow analysis, and then Chapter 7, rate of return analysis, and incremental analysis. So each of those gave us different ways to either analyze one alternative or multiple alternatives. In Chapter 9, we're now going to learn a few more different types of analysis methods. So instead of just spending the whole chapter on one of these, we're going to really focus on 4 different types of analyses within this one chapter. So let's briefly talk about what these 4 methods are. The first is something called future worth analysis. The second, benefit cost ratio analysis. The third, payback analysis. And the last, sensitivity and break-even analysis. So the reason they kind of lump these into one chapter is because none of them is very difficult by itself, and they're all very similar to the ones that we've done before. So that's why in this chapter we're going to learn 4 smaller analysis methods all at once. Okay, so as we get started, we're going to first focus on future worth. So the way to think about this is a future value problem is one where we know how much we're going to invest today, or how much we're going to invest over the next n years. But really, we want to figure out how much our investment will grow to in n years from now. So future worth analysis then is computed the same as the present worth analysis, except for that we want to solve our cash flow diagram for an f value instead of a p value. So in functional notation, all of our f given p or our f given a, we're now going to want to solve for that f value. And we did this a little bit early on within our functional notation, but we're just going to kind of build on that same type of analysis. So there's 2 methods for solving for future worth. One is to convert one value at a time to a future value. So you draw your cash flow diagram, you just take each little arrow on your cash flow diagram and you convert it to a future value. The other method then is to convert all values to a present worth value first, and then convert that present worth value to a future worth value. So you can do either or. Some problems call for the latter, and we'll talk about that in a minute. But the other thing you have to take into account is that if I convert everything to a present worth first and then to a future worth, there's going to be a lot of factors going on and a lot of rounding, and so sometimes you'll get different answers. But either one of these methods is really acceptable. Okay, so let's look at some examples for future worth analysis. Suppose you buy and sell a piece of equipment. So here's our cash flow for that equipment. A purchase price of $16,000, a sell price in 5 years from now of $4,000, so that's probably my salvage value, right? An annual maintenance value of $3,000, and a net profit contribution of $6,000, and then a minimum attractive rate of return of 12%. So with all of this information in mind, what is the future worth of the equipment? Okay, so once again, you can do this in a couple different ways. We're just going to go through both of these methods to solve this problem. Okay, so I'm going to draw a cash flow diagram. Once again, I feel like this always helps me. So I'm going to draw this initial cost of $16,000, a contribution yearly of $6,000, and a maintenance cost of $3,000, and then a salvage value or a selling value in 5 years from now for $4,000. So I have this cash flow, and really I want to find out what cash flow is going to be equivalent to that gives me this future value over here at year 5, or this future cost at year 5. And it might be a benefit. I just already know it's going to be a cost, so I drew my arrow that way. But I'm going to solve this whole cash flow to find out the equivalent cash flow in a future value. Okay, so I'm going to say method 1. Method 1 then is going to be converting each individual value to a future value. So here I have my negative $16,000 right here, which is a present value, so I want to convert it to a future value. Then I add $6,000, and that's a uniform value that I want to convert to a future value. And then I have negative $3,000, which is a cost, which is an annual cost I want to convert to a future value, or a uniform cost I want to convert to a future value. And then I add on my $4,000, which already is a future value happening at year 5, so I don't have to convert that value at all. So really nothing here has changed, nothing's really new, it's just what we're solving for in this cash flow diagram is now different. Okay, so if you notice I use that minimum attractive rate of return of 12% right here in this functional notation to help me solve for my future worth. Okay, so I find those individual factors and I solve and I get a future worth of negative 5133. So this whole cash flow diagram right here would be equivalent to a future value or a future cost of $5,133. Okay, so let's do method 2 and see if we get a similar answer. Okay, so same idea. So I'm going to say method 2 then is going to be to convert this whole cash flow right here to a present value first. And then after I find one lump sum of a present value, I'm just going to use one factor to convert that to a future value. Okay, so I say negative 16,000, which is a present value, so I'm not converting it at all, plus $6,000, which is a uniform cost and I want it to be a present worth, minus 3,000 times a uniform cost I want to convert to a present worth, plus $4,000, which is a future value that I want to convert to a present value. So I find those factors and I get that equal to negative 2917. Okay, so now I'm going to convert that negative 2917 to a future value using just this functional notation formula right here. So I find that factor and I get negative 5139. So you'll notice that answer is slightly different than the one that we found before. It's $6 more or $6 less, I guess, depending on which way you look at it. However, just keep in mind all of the converting that we have done. Okay, so all of these different factors here, there's been a bunch with present worth, there's been a bunch with future worth. So this is what I was talking about before with you can sometimes have error when you do all the converting to present worth and then to future worth. So either way you'll get an answer that's within a ballpark. Like $6 when we're talking about $5,000 is not a huge deal, but it's still a little bit different. Okay, so now let's look at a different example. A 20-year-old student has decided to set aside $100 on his 21st birthday for investment. Each subsequent year through his 55th birthday, he plans to increase the investment on a $100 arithmetic gradient. He will not set aside additional money after his 55th birthday. If he can achieve a 12% rate of return, what is the future worth of the investments on his 65th birthday? Okay, so I'm sure you get what's going on. Someone at age 20 puts $100 in a bank account every year, and then he increases that amount by $100 every year until he is 55. And then he quits putting money into this account, but he lets all the money sit there until he's 65. And we want to know how much money is in that account when he turns 65. This sounds like a good real life problem, right? Like maybe a save for retirement problem or save for travel problem. Okay, so let's start talking about this problem. So I'm just going to give you the hint, or rather you can look in the back of the book and prove it to yourself, but there is no F given G column in the back of your book. So if you have some problem that's a gradient, you can't really just directly convert that to a future value. So whenever there's a gradient in the problem, you have to convert it to a present value first and then to a future value. So that's one area where you don't really get the choice on how to solve it. I mean, I guess you could because there's a formula you could use, but the formula is a little nasty. So I would just recommend whenever there's a gradient, use the present worth approach to solving for the future worth. So with that in mind, let's look at this. So I'm going to say my present value is $100, so that's my uniform cost, right? I'm going to put $100 in every single year, and that's going to be for 35 years. On his 21st birthday to when he turns 55, that's 35 birthdays. So I'm going to add to that $100 times a P given G gradient also for 35 years. So remember that money is then increasing $100 per year until he's 55. Okay, so I find those individual factors and I get $7,078.10. So that's how much all of that money I'm going to be putting into this bank account is worth right now, $7,078.10. Okay, so now let's convert that to a future value. So the difference this time is going to be how long. So up here I use 35 years in my calculations, but down here I use 45 years in my calculations. And that's because down here this money's sitting in the bank for those 35 birthdays, but also for 10 years longer. Versus up here, he was just depositing this money into the account for 35 years and that was it. So here I'm going to take into account this money sitting in the bank for 10 extra years. So I'm going to find F given P of the $7,078 and I get that is worth $1,160,723.46. So to me this is kind of a good example of maybe how you could figure out how to save for retirement, right? If when you retire at age 65 you could do this same kind of idea. So this is actually useful material.